Hello, my name is Casey Benhart. I work for the ABB HVACR Applications Engineering team. Today, I'd like to talk to you about the important considerations when selecting a motor and VFD. By the end of this presentation, you'll be familiar with the selection criteria for variable frequency drives as well as motors, and have the ability to educate others regarding the best solution for their applications. For our agenda today, we'll look at the selection information, including supply voltage, as well as motor voltage, FLA, and horsepower. We'll look at NEMA MG Part 31.4.4.2 and cable distance. We'll look at the different motor technologies, old motor considerations, output side filters, disconnect, bypass, and redundant options, the environment and derate considerations, enclosure options, I/O and protocol support, Bluetooth and non-Bluetooth control panels, when to consider harmonic mitigation options, and talk about the expanded capabilities of the ACH 580 drive. We'll then end with talking about installation, specifically shielding, control cables, grounding for the VFD and grounding for the motor, and why you should use VFD cable. We'll also look at multiple motor considerations, and then we'll wrap up with an overview of the topics discussed. We begin drive selection by understanding the supply voltage. This is fairly straightforward, being that low voltage AC drives in North America are typically rated for 200 to 240 volts to support 208 to 230 volt motors, or 440 to 480 volts to support 460 volt motors, as well as 500 to 600 volts to support 575 volt motors for HVACR applications. It is also critical to understand where the supply voltage is at in its range, as well as if the supply to the drive is a single phase or three-phase input. The lower the supply voltage, the higher the amp draw will be. A single-phase supply will require significantly more amps to power that motor. ABB drives will supply a three-phase output to the motor regardless of whether it's supplied in single-phase or three-phase input. But consult your hardware manual to ensure that the drive is able to support the output current needed, as well as the voltage that the motor requires. Now let's take a look at your motor nameplate. What is the motor voltage, the FLA or full load amps, and the horsepower of the motor? Make sure the VFD current rating is equal to or greater than the motor nameplate FLA. If the VFD power rating is lower than the motor power rating, check with ABB or just upsize to the next size larger VFD that is rated at that power. Keep in mind that a motor's service factor is always 1 when supported by a drive, regardless of the nameplate value. Now let's look at multiple motors being supported by one drive. If you have a drive that will be supporting multiple motors, there are a few things to consider when selecting the drive. Though the motors don't have to be equally sized, a separate overload is needed for each motor. The drive must have the capacity to support the combined FLA and total horsepower of the motors that are being supported by the drive. So you'll need to add them up and ensure the drive has that capacity. Ensure that you verify whether the motor you are selecting is inverter duty rated. An inverter duty rated motor will satisfy MG1 Part 31.442. This rating has a specific requirement for the insulation in the motor. Motors rated for 600 volts or less must have an insulation that can handle a voltage magnitude of 1.1 times 2 times the square root of 2 times the voltage rating for the motor. That 1.1 is a fudge factor. The 2 accounts for the reflective wave and the DVT overshoot. Square of 2 converts the rectification of AC to DC in the drive. And the last factor is the rated line-to-line voltage. If we look at a 460 volt motor, we would have an insulation rating that could handle 1431 volts. Now note, motor insulation temperature ratings are not mentioned in NEMA MG1 Part 31. So do not mistake temperature ratings with the actual voltage ratings. Now why is MG Part 31 so important to verify? Well, when a drive powers a motor, it uses pulse width modulation to recreate the AC waveform to provide the power needed for the motor. To recreate the AC waveform, pulse width modulation uses pulses of positive and negative voltage and specific frequency. In this process, the square waveform created that are part of the PW waveform will have some overshoot and will create ringing. The longer the cable distance between the drive and motor, the bigger this overshoot. Impedance mismatch is caused by capacitance in the cable between the drive and the motor and increases with length. There is impedance mismatch at the point the cable attaches to the motor. This, in turn, creates voltage reflection as a waveform travels the length of the cable. This results in voltage spikes. NEMA MG Part 31 is accounting for this in its calculation. In the ACH 580 hardware manual, the following information is published regarding cable lengths. This is for protection of the drive and identifies the optimal cable length. For multiple motors, the calculated sum of all motor cables tying back to the drive must not exceed the maximum motor cable length given in this table. Now, each motor manufacturer have published information as far as acceptable cable length, so check with your motor manufacturer to understand exactly what is allowable for that particular motor. Clearly note also that the larger horsepower drives accept longer cable lengths rather than the lower horsepower drives. This chart does not take into account the addition of a DVDT filter. Now let's take a look at the different motor technologies we compare with the drive. We'll begin with induction motors. These motors are the most familiar and proven technology in electric motors. They now come with the ability to satisfy up to an IE4 international efficiency standard. They have the ability to run directly across the line, which means they can operate without a drive, or they can be paired with a drive and bypass package. They're easy to use and maintain, but they do have the drawback of their speed accuracy without sensors, and also have slip loss in the rotor, which adds to heat in the motor and bearings. They also have lower efficiency at low speed and partial loads. Next, we have the synchronous reluctance motor, which can satisfy up to the IE4 international efficiency standard. These operate at synchronous speed. They have low bearing and winding temp, high power density, and are magnet-free and easy to maintain. They do require a VFD to run and have high current demand and low power factor. Next, we'll move to interior mounted permanent magnet motors. These have very high efficiency, high torque density, excellent power factor, excellent torque to inertia ratio, and excellent partial efficiency loads. But they are typically made with rare earth magnets and tend to be high cost and somewhat difficult to service because you have to lock out the shaft, because if you have something free spinning, it can turn into a generator. Next, we'll talk about ferrite-assisted synchronous reluctance motors, which share a lot of the characteristics of the interior permanent magnet motors as well. They're very high efficiency with IE5+. They operate at synchronous speed. They do use ferrite instead of rare earth metals, have excellent power density, maintain efficiency at low speeds and partial loads, but they also require a VFD to run. All of these different technologies, depending on your type of application, your focus on efficiency or operation may be the right choice in selecting and pairing with the drive. And the ACH 580 drive has the ability to manage and operate each of these different types of technologies. It's not uncommon in a retrofit situation where you're putting a VFD in place of a starter or stop starter to run into an older installation of motors. These motors may be compliant to the NEMA MG Part 30 standard. In this case, they'd be designed to work with a 60 Hz sine wave with a peak voltage of only 1000 volts and a rise time not less than 2 microseconds or a DVDT less than 500 volts per second. In these cases, they are not inverter duty rated motors, so it's very important to account for the cable distance that's associated with the distance between the drive and the motor. In these applications, if you don't take account of this, you're exposed to insulation failure or overheating. Now, what is a long cable distance when it comes to these types of motors? Well, small motors may be 25 feet or less, larger might be 100 feet or less, but there's a lot of variables that impact the measurement and capability. The motor manufacturer has the final say on what the motor can actually handle. So when in doubt, reach out to the motor manufacturer for a consult, and they may recommend a DVDT filter. There are 3 different industry solutions that protect both the motor and drive from reflective voltage waves. These are An output filter, which is the most basic solution, typically applied to distances less than 100 feet. A DVDT filter, which can support up to 1,000 feet and is a great balance of cost and performance. And a sine wave filter, which can support thousands of feet and have a high cost but great performance. Please note that a sine wave filter cannot be used with a motor that is using vector control. This would include synchronous reluctance, PM motors, as well as Farad-assisted synchronous reluctance motors, because they restrict the drive's ability to sense the motor and calculate the speed control of that motor. So as we take a look at our review of the variables when selecting a new motor, we want to verify that it's an inverter duty ready motor. So verifying that it supports NEMA MG part 31.4.4.2. If it states just inverter ready, check for caveats. There's often motor manufacturers that don't fully satisfy the NEMA MG part 31 requirements, and they will sometimes publish an inverter duty ready notification on the data sheet for a motor, but it may not actually support and be robust enough to actually handle inverter applications without taking some type of mitigation on the output side of it. Verify what the cable distance is, understand the horsepower size of the motor, understand whether you're going with a single motor or you're supporting multiple motors, and take that into account in establishing if you need any output side filtering going on there, whether it's output DVDT or sine wave filter, and ensure that you pick the right motor technology, that it satisfies the speed range, satisfies the type of loading at slow speeds, and understand how the motor cooling will take place, how slow the application actually handle, and your target efficiency. Also think about things like whether or not the application needs the ability to have a bypass and whether it can support a 60 hertz operation in a bypass condition as well, as far as the rest of the system. When we're looking at selection for an old motor, it goes back to understanding the age of the motor itself, what it actually satisfies. If it is not inverter duty ready, taking into account exactly what the cable distance is, understanding that you need to reach out to the motor manufacturer to verify what's acceptable for that motor, and ensuring that you select the drive package and program that accordingly and put any output side mitigation in that's necessary to support that motor's capabilities. Let's take a look at a couple of the options that can be packaged with the drives. A standard disconnect option gives the ability to isolate the drive from the incoming power. You can select a vertical or box style bypass that will provide the ability to bypass the drive while still having the ability to see all three phases and protect the motor. You can have this include options such as a service switch or soft starter for soft ramp and elimination of inrush current. You can also pick a redundant drive package option with a single point connection and disconnect, terminal blocks that provide a single point connection for interlock, start, and speed signals, a lead drive selector switch, and the ability for remote transfer between one drive to another through the building automation system. Let's discuss the different enclosure options for the ACH 580 drives. We'll begin by looking at UL Type 1 enclosure. This is designed for indoor use. It is finger safe and prevents the ingress of objects and falling dirt, but is best applied in clean and dry environments like a conditioned mechanical room. Next, we have UL Type 12, another indoor design that provides a bit more protection from hazardous parts of the drive, ingress of dirt and fibers, and can protect against light splashing. This is best applied if you're still in pre-construction and may have dirt and dust in the environment. There's a NEMA 3X and 3R, which can be for indoor or outdoor use. This is the most used enclosure for outdoor applications. It protects against ingress of water and includes a heater and can be upgraded to stainless steel. Now we have the NEMA 4X, which is designed for outdoor or indoor applications. It can handle almost anything you throw at it, but should have a sun shield attached if it is going to be sitting in direct sunlight. Please keep in mind that this unit is not packaged with an air conditioner or heater, so derate conditions will apply to it. And last, we have our NEMA 4 and 4X packages, which are designed for indoor or outdoor use. These are packaged with a heater and air conditioner, which will mitigate some derate conditions, which we will discuss next. But in each case, remember to evaluate whether or not you really want to put a drive in a location that requires a heater or air conditioner. The drive, if installed and maintained properly, will outlast any air conditioner installed in the enclosure. So let's talk about the topic of derate. Derating is determining the new maximum output current rating of a drive less than its nameplate due to the environmental conditions, the operating setup, and/or an input power source. With environmental conditions, it's going to be the ambient air temperature or altitude. With operating setup, it's going to be the drive carrier output frequency. And on the input power connections, it's going to be whether you're working off a single phase input voltage or an open delta supply transformer. Derating provides us an accurate way to account for these factors to determine the output current that a drive will be able to support when faced with these conditions. Remember that we don't size a drive off of horsepower alone. We need to take horsepower and output current into account. The goal of the derate is to determine if the correct size of drive is selected for this environment. We'll begin our derate calculations with altitude. There are two impacts that high altitude has on the drive operation. The first impact is on cooling. The second is on electrical component spacing to prevent arcing. At high altitudes, the drive has lower cooling efficiency due to thinner air density passing over the heatsink. Drives are rated for 3,300 feet, or 1,000 meters above sea level with no derate required. Above 3,300 feet up to 13,200 feet, a 1% reduction of the drive output current and the output power occurs for every 330 feet increase in altitude. The impact on spacing is that at high altitudes, the air density decreases, allowing electrical arcing to occur more easily. Now let's take a look at temperature. VFDs produce heat from the diode bridge and the insulated gate bipolar transistors. Installing a VFD in an already hot environment may require a VFD to be derated to allow it to dissipate heat more efficiently. The standard ACH 580 nameplate rating is valid for ambient air temperatures from 5 degrees to 104 degrees Fahrenheit. This applies to UL Type 1 and Type 12 enclosures. NEMA 3R enclosures can operate from 0 degrees to 104 degrees Fahrenheit. For operating ambient temperatures of 104 to 122 degrees Fahrenheit, you need to derate the maximum output current by 1% for every 1.8 degree Fahrenheit above 104 degrees Fahrenheit. For configured UL Type 4 and 4X packages mounted inside or outside the ambient air temperatures of 104 degrees Fahrenheit, derating the drive by 1% rule doesn't apply because the air conditioners that are used in those particular packages. The air conditioners may require to be oversized for installations of ambient air temperatures greater than 104 degrees Fahrenheit. Altitude and temperature can be used to avoid a derate. If an ambient temperature is below 104 degrees Fahrenheit, the derate can be reduced by 1.5% for every 1.8 degree Fahrenheit reduction in temperature. So for an example, if I was in Albuquerque, New Mexico at an elevation of 5,312 feet with an ambient temperature of 85 degrees in the location that I'm installing the drive, if you're installing a 124 amp ACH 580 drive, you would have to derate around 6% based on the altitude, knocking the drive rating down to 116 amps. But with the temp being 19 degrees under the 140 degree Fahrenheit, the rating for the drive would then increase back up to 117 amps. You would be able to subtract around 15% of that derate of 8 amps, so that it would end up being 7 amps instead. This is a specific example, but you have to remember you can't use this analysis to get more current out of the drive than the maximum label rating. Carrier frequency, also known as switching frequency, is how fast the drive will turn on and off its output transistors. Turning transistors on and off produces a lot of heat. Most HVACR applications have their drive's default value around 4 kilohertz. When you increase the switching frequency to, say, 8 or 12 kilohertz, more heat is produced, and thus a derate consideration of the drive needs to be evaluated. This is dependent on horsepower and the rating of the voltage to the drive. Consult your hardware manual to correctly evaluate this. There are other solutions such as having the drive monitor the heat seat temperature and automatically reduce the carrier frequency as the temperature increases to avoid overheating, but this needs to be evaluated whether it's appropriate for the application you're supporting. The last derate condition we're going to discuss is a single-phase input for the drive. In this case, you have only 2 conductors instead of 3 supplying voltage to the input. This results in an input current for the drive being much higher. A single-phase input delivers 1.73 times the current of a 3-phase input. In other words, it's almost twice as high. This means the diode bridge will be seeing higher currents than it was originally designed for, and you'll see the DC bus having a higher ripple current, creating extra heating for the bus capacitors. In this situation, you will typically double the size of the VFD you select. By selecting a larger drive, you increase the bus capacitance able to store more energy, thus reducing the DC bus ripple. In each of these different derate scenarios, it's critically important that the correct wiring and fusing be selected for the resulting drive that is applied to the application. Now let's take a look at the I/O that's needed for your application. Now the standard ACH 580 has plenty of I/O available, including 2 analog inputs, 2 analog outputs, as well as 6 digital inputs and 3 relay outputs. The ACH 580 also has an I/O expansion module capability. In its expansion slot, you could place a CA-IO-01, which will give you an additional 3 analog inputs and 2 additional analog outputs. You could also install a CMOD or CMOD-01, which gives you 24-volt AC-DC input power to keep the control board energized, 2 additional relay outputs, and 1 additional digital output, or the CHDI-01, which would provide 6 additional digital inputs, which are 115 volt to 230 volt rated inputs, along with 2 additional relay outputs. The CA-IO-01 expansion module applied to the ACH 580 drive provides you with a total of 5 analog inputs, 4 analog outputs, 6 digital inputs, and 3 relay outputs. These additional analog input and analog outputs are very valuable when you apply the ACH 580 to any standalone application where you might want the drive to manage a process. This includes cooling towers, air handling units, chiller condenser loops, and many other applications that require expanded analog input and output capacity. The CMOD-01 provides a very important feature in its 24-volt AC-DC input power capability that it provides to the control board. If connected to a UPS system in the event of an input power loss, both the field bus and serial communications will remain active. It also provides 2 additional relay outputs for expanded process control and a digital output if you need to communicate to pilot lights, alarms, auxiliary relays, solenoids, or a PLC digital input module. For some new and also legacy applications, if you have a process that includes devices or reference points between 115 to 230 volts AC, the CHDI-01 can provide 5 digital inputs to support this, along with an additional 2 relay outputs for expanded process controls. What protocol support do you need for your application? The ACH 580 drive has several embedded field bus protocols that are standard on this product. These serial communications include BACnet MSTP, Johnson Controls N2, Modbus RTU, and GP1 General Protocol. For additional support, there is an F serial module that can be added to support other protocols, including LonWorks, BACnet IP, Ethernet IP, Modbus TCP, as well as legacy industrial protocols such as Profibus and DeviceNet. The ACH 580 drive has a Bluetooth control panel as a standard. It also has an optional non-Bluetooth control panel available as an option. Both support primary settings for most common features, making the commissioning of a drive fast and simple, as well as having a help button for problem solving. They both support a USB interface for PC tool connection as a standard, and it's possible to move information between PC and drive with no extra hardware. Both have hands-off auto functionality that ensures that all control and flexibility in the drive's operation is available to users. Drive settings can be stored to the control panel for a simple backup and for programming additional drives. There are several features you can use with the Bluetooth control panel. The Bluetooth on the panel is not active unless someone presses the question mark on the keypad on the control panel for 3 seconds. It activates Bluetooth on the panel and provides a random 6-digit PIN. You have to download the DriveTune app, which is free on iOS and Google Play stores. With this app on your mobile device, you can open the app and select Pair to Drive. You'll need to enter that 6-digit code and it will create a one-time connection to the control panel. You can then safely move away from the drive from a range of up to 30 to 60 feet and do whatever commissioning, troubleshooting, or maintenance to the programming that is needed. It also has the ability to stop, start, and put the drive into auto. Once you complete your session and disconnect, the Bluetooth on the panel is disabled, and you have to push the question mark again to reactivate it. It will generate a different 6-digit code to be able to connect again to the app. This can be a valuable tool for interfacing with the drive, but please keep in mind that if you are selling to anyone who restricts Bluetooth technology, such as a data center or government facility, please select the option of a non-Bluetooth control panel. Harmonics are an important topic to consider when looking at drive selection for any installation that has sensitive equipment. This includes medical equipment, airport electronics, security systems, communication equipment, and laboratory research equipment. Harmonics can cause interference to electronics that have carrier signals, such as lighting systems and power meters. Generators may have voltage regulator issues when loaded with high harmonic content. Harmonics can cause hardware to run hotter as well, impacting transformers and motors that are in the system that are run directly off the line. Most of the common sources of harmonics in HVACR applications are electrically commutated fans, VFD-driven fans, pumps, and compressors, photocopiers, PCs, domestic appliances, UPS systems, and LED lighting. Essentially anything with a switching power supply. But there are some general rules that can be followed to simplify how to evaluate whether you need to consider harmonic mitigation solutions. IEEE 519 is a common standard that is enforced by utilities that sets guidelines for both current and voltage distortion. If you have a job that has anywhere close to 30% of a nonlinear load on the transformer or generator, you should look to do a harmonic analysis. ABB has tools that can assist with this analysis. What will be needed is a schedule of the VFDs, the transformer data including the kVA and percentage impedance. But if you have a large transformer and small amounts of nonlinear load on that transformer, harmonic mitigation won't need to be the focus. Microdrives and EC fans will typically produce around 72% plus total harmonic distortion. A standard 6-pulse ACH 580 drive has a dual DC choke after its diode bridge in front of its DC bus that will lower the total harmonic distortion produced to around 35 to 45%. You can also order an ACH 580 drive with a passive filter in front of it. This will lower the total harmonic distortion to 5 to 7%, but requires some space and tuning considerations. The most robust solution for harmonic mitigation is the ULH drive. The ACH 580-31 will lower the total harmonic distortion to less than 3%. This can also hold unity power factor to around 20% load. As we discussed, the standard 6-pulse drive is typically going to facilitate the needs of most installations. But if there are sensitive equipment in the job, or there's a transformer that has a lot of nonlinear load on it, the ULH is the best solution. Please also consider that the ULH drive has the ability to do power factor correction. Please ask your drive specialist or applications engineer if there are any questions about these features. Please keep in mind while selecting your drive that the ACH 580 drive series has the most comprehensive range of HVACR software features on the market. From the most basic to the most advanced, we have standard software features in that drive to support your application. We also have technical notes out on ABB Now, drive specialists, and applications engineering team to support these capabilities. Now let's talk over some of the tools that you can use to help organize the information for your selections. The first tool I'd like to discuss is the VFD schedule generator. Now, what is the VFD schedule generator? It's an Excel-based tool with no macros. It can be easily modified because it's not password protected. You can populate the data, and then essentially you can use it to copy and paste into CAD programs. It includes frequently asked questions and instructions in general. Why would you use it? You essentially can use it to organize everything as far as your VFDs, has spaces for populating your transformer data, your generator data as well. And then you can also use it to organize if you need to take an approach of doing a harmonic analysis as well. We also have the product configurator out on ABB Now. Now this particular tool is quite robust. As you go through, you select your voltage, you select your nominal horsepower, you can select your enclosure rating, what type of harmonic mitigation you may need. You select your disconnect type. If you want a bypass option, you can select those specific options as well. The product configurator then allows you to select your other options and field kits as needed, including control panel options, selecting if you were supporting multiple motors, power options, as well as your connectivity and I/O options. After entering this information, you can select the Documentation tab to see the dimensional and electrical drawings, and if you select Add to Quote, you can get a pricing and proposal package for your selection. Proper installation of a variable frequency drive and motor are critical to have it successfully support an application and have optimal performance. There are many shortcuts that have been taken in the past that a drive and motor can still function in, but this will shorten their lifetime and lead to inconsistent performance and more downtime. Shielding should be part of the control, input, and motor cables. You should never route control cables in conduit with any power. Make sure you have the right distance between your mains, motor, and control cables. Grounding is critically important for both the VFD and the motor. Always look for 2 grounding connections for a VFD, at the building's electrical network ground and the motor ground wire. Never daisy chain grounds. Each VFD must be individually grounded to the building's grounding point. For motors, run a ground from the motor to the VFD in addition to any safety ground. Take advantage of the metal conduit as an additional grounding path. Keep in mind that drives produce high-frequency noise on the output side that wants to find its way back to the source. There are multiple types of motor wire used in HVACR applications. We begin with THHN, which is the most commonly used motor wire in the industry. Unfortunately, it's also the worst of the quote-unquote acceptable motor wires used for VFD and motor applications. It typically has an inconsistent jacket and provides less insulation than other options. There's also XHHW, which is a better solution, suitable for wet or dry environments, and has a better insulation value and heat resistance than THHN. But the preferred solution for any VFD manufacturer is VFD cable. This is symmetrically shielded cable with 3 phase conductors and symmetrically constructed PE conductor and a shield. It provides the best quality for the application and helps reduce the chance of capacitive coupling. For multiple motor installations, there are some additional considerations we need to account for. As we discuss, the motors for this do not need to be sized equally, but there is a requirement for a separate overload protection for each of the motors. The drive has to have the ability to support the total FLA and horsepower of all the motors combined. You'll be using scalar mode to operate these motors. The cable distance from the drive to the motor for each motor must add up and cannot exceed the maximum published cable distance identified in the drive manual. You'll disable Energy Optimizer to simplify the motor control, and you should always have dedicated conduit for each motor. You also need to keep the switching frequency to 4 kHz. One last consideration should be that internally mounted permanent magnet motors should be avoided when it comes to multi-motor applications. Now let's review. We understand that we have to evaluate the supply voltage that's being provided to the drive. We need to understand the motor voltage, the FLA, and the horsepower requirements for that motor. We need to evaluate the cable distance to protect both the drive and the motor and select the right motor technology for the application, as well as the right options for the drive package. We understand the different factors that may require us to derate the drive's amp and horsepower ratings and the enclosure options that might be needed for the environment the drive will be installed in. We have reviewed the different I/O and I/O expansion capabilities along with protocol support for the application. We also know when to select a control panel with or without Bluetooth capability. We have also gained an understanding of how to evaluate whether or not you perform a harmonic analysis and if any mitigation should be put in place. ABB has tools to help organize this information with our VFD schedule as well as our product configurator. We have also reviewed the important installation considerations for both the drive and motors, including shielding, control cables, grounding for both the VFD and motor, as well as why you should use VFD cable and what to consider when selecting multiple motors. Thank you for your time and attention to this presentation. If there are any questions, please follow up with your local drive specialist or applications engineering team member.